Hello, everyone. Welcome back to the AAS YouTube channel. And this one is in the ebook series. And I am super happy to have ebook author Sally Dodson-Robinson with us today. Hey, Sally.
Hi.
Well, I'm doing super well today on February 17th, 2022. Where are you located at, Sally?
I am in Newark, Delaware.
Newark.
Sharp Lab specifically.
Okay. Is there snow on the ground there in Newark?
There was over the weekend, but it's almost all melted by now.
All right. Probably a little early for spring, though.
Yeah.
Yeah, a little bit. You probably get a snow or two. Plus, there's that big northern air mass coming down.
Right.
It cooled off Phoenix pretty well yesterday. I mean, we didn't see snow or Phoenix, but
Sure.
but it cooled off pretty good for Phoenix. So I imagine
That's
it's
nice.
to the east, so you might still get another Arctic blast here in a day or so as that moves across.
Maybe so.
Yeah, cool. You are obviously in your institutional home office, and you have some awesome binders over your left shoulder. What are those?
Those are my notes from grad school.
Oh my gosh.
Yes.
That's wild.
And some of them aren't notes. Some of them actually contain papers that I printed out and I read, in the analog format and not the digital format. And they have highlights and everything.
Very cool. Yeah, I can remember doing that. Where did you do your grad work at?
I went to UC Santa Cruz.
So did I. Hello, banana slug.
Banana slugs, yeah.
So I actually did the same thing as you did, except my binders were red, and I had
okay.
class notes in there, and yes, and just to date myself a little bit, but when I was going to Santa Cruz, at least in the first couple of years, if you wanted the literature, you still had to go in and crack open a physical copy of APJ or HA or something like that. ADS and the internet were not quite where they are now, but
okay.
Very cool. So that's why I had all those binders, notes, and things like that. So Sally, what do you like to do for research?
Well, most of my work has been in giant planet formation, but for the past couple of years, my active research has been transitioning into detecting Earth-like planets around sun-like stars.
Cool.
So I get to write about giant planets, which one of my favorite subjects, and then research-wise, I get to work on radial velocity surveys, which is actually what I started with in grad school and what I was part of for my master's degree. And so it's really great that I get to do both.
Very cool. Very cool. Very cool. So how did you get the idea to do an ebook, or how were you approached about doing an ebook or something like that?
Yeah, actually I was approached. So I got an invitation to write about giant planet formation from the commissioning editor. And I knew that I had wanted to write a book. That was a career goal. And so when I got approached, I just thought, okay, well, I guess now is the time. So let's do it.
Very good. Very good. Well, you can cross that one off your bucket of things to do.
Mm-hmm.
Very cool. How long did it take from once you were approached to when you finished? This is maybe what, a 1 week, 2 week process?
Let's see. So I signed my contract in, I think it was August 2018.
Okay.
And I had proposed my own timeline, which without any guidance, and I decided that a year was the right time frame to write the book, and I was wrong. Okay. I actually submitted the final manuscript in April 2021. And so that's when, I think it was April. And then shortly after that, it was accepted. And then, it was in press after that. So finally we're, 3.5 years on from when I signed the contract. Yeah.
Very cool. Very cool. Yeah, I think sort of that 2 to 3 year time scale is sort of a common theme among people.
Yeah.
So just for prospective authors out there, just so you get a clearer view of what the time scale is to do these things, particularly with the job one wants to do. So
yeah, I had never done anything so extensive before, and I didn't really have a baseline for what the writing process would be like, how long it would take.
Yeah, very cool. Yeah, I imagine it's a bit different than writing, let's say, a research paper, right? APJ, something like that. So yeah, it's a different. So speaking of, what is the target audience for the ebook? Who's it for?
Yeah, well, I sometimes teach classes in planetary astronomy to advanced undergraduates, and earlier career graduate students.
Okay.
So they are combined levels. So I teach at 2 levels at once, and one being the senior undergrad level and one being the introductory grad student level.
Mhm.
And those were the people that I had in my head as I was writing the book. So I was thinking, what can I do to make it easier for these students who I've had in this class before to understand the subject?
Mhm.
And I don't teach, I mean, I teach planet formation in my class, but it's really a survey of planetary science. So it was nice to drill down into planet formation.
Cool.
And the other thing that I was trying to achieve was I wanted to put together a resource where if a student really works through the book, they come out the other end ready to start their own research. Like they're just ready to jump into it.
Cool.
That's what I was trying to achieve. So readers can tell me if it worked or not.
Okay, there you have it. People, give her some feedback. Very cool. So with that, why don't we go ahead and take a look at the ebook and walk through it a little bit and see what we got. We have Origins of Giant Planets, Disk, Dust, and Planetesimals, Volume 1. And Sally, take us away.
Okay, well, I would first like to look at the dedication to this book,
Okay.
if you could show that. So this book is dedicated to Peter Bodenheimer, who was my grand advisor in grad school. So he was my advisor's PhD advisor. My advisor was Greg Laughlin.
Okay.
And those two were both terrific, and I worked with both of them. And when I was finishing my PhD in 2008, Peter's star formation book was in press.
Right.
And a bunch of students asked, was he going to write a planet formation book? And he said, no, because we don't know enough yet. And so when I got this request to write a book in 2018, I decided, okay, it's been 10 years. We probably know enough. So this is the book that I wrote because Peter didn't do it. If Peter had written it, I doubt that I would have needed to do it.
Well, that's a shout out, Peter. Hi.
Yeah.
And to Greg as well. Very good. Very cool.
Yeah. So in the first chapter is actually about the scientific legacy of giant planet research.
Okay.
And what I really wanted to do was to give people a reason to care about this subject. So I wanted to answer the question, so what? Why does this stuff matter? And in the history of Western Europe, it mattered tremendously. So, I mean, Galileo was put on trial by the Inquisition for the consequences of his planetary astronomy. And Katharina Kepler, Johannes Kepler's mother, was actually arrested and put in prison for more than 1 year on suspicion of being a witch. And her conviction for witchcraft was partly a result of Kepler's work. And particularly, he actually wrote a science fiction novel about giants living on the moon. And some people consider it the first science fiction novel ever written.
Okay.
And it landed his mother in prison.
Hmm.
So, you know, this type of thinking, investigating other worlds out there and the consequences of that research, understanding that Earth is one among many planets, these had huge personal consequences for the people involved in this study.
Yep.
And then the political ramifications were huge. I mean, this was shaking the control of the Catholic Church in Europe. And then just in terms of the mathematics that were developed in order to understand giant planet orbits, I mean, these feature strongly in Isaac Newton's work. So first theoretical physics textbook ever written, according to Neil deGrasse Tyson, I think. So Newton's Principia Mathematica. So, you know, and it was largely motivated by planet research. Same with the calculus tools that were developed by Lagrange and Euler. I mean, these were developed to explain giant planet motions, and of course, Earth moon motions as well, Mars, etc. But this topic, it's interesting for us, and it's something that we enjoy exploring as researchers, but our lives aren't at stake. but in the past, people's lives were at stake because of this type of work. And so I just wanted to connect with how powerful this topic has been throughout history. So I had a lot of fun with chapter 1.
Cool.
And I hope the readers will enjoy it too.
Cool. Very
yeah. And actually, so the first figure in this book.
Yeah, let's take it. You want? There we go.
Yeah.
Oh yeah, sure.
So this is actually a scrap paper that Galileo wrote on, and the top part above the line is a draft of a letter, but then below the line you actually have sketches, and so the circle with the asterisk in it represents Jupiter, and then the little stars off to the side with the arrows beside them, that represents, 4 of them, that represents the motion of the Galilean satellites. And so this is actually Galileo working it out, drawing it out, figuring out how these orbits work, figuring out that actually these satellites orbit Jupiter, they don't orbit the sun.
Right.
So, I mean, I think this is really amazing. And just looking at this image, it's kind of an incredible experience to be able to see this.
That's a great copy of that document. Yeah.
It's beautiful. The digital restoration, people did a good job on it.
Fantastic job with that.
Yeah.
Very cool.
So in chapter 2, I go on to the planet forming environment.
Okay.
And so that is protoplanetary disks.
Yes.
Yeah, and this is actually my specific area of expertise in planet formation. So this is what a lot of my papers are about, are disk models.
Cool.
Yeah, and so I start first just with the evolutionary phases of disks, because I want people to be able to picture in their mind a disk at the beginning of the planet formation process, and a disk that's midway through, and then a disk that's just starting to dissipate, and the planetary system is almost all formed. So we go through that in section 2.2, and excuse me, there's actually a figure with spectral energy distributions of disks in chapter 2, and which figure is that one? Let us see. Oh, so that one is figure 2.3.
Yep. How about that? I got it.
Yeah. And so this is what I want people to carry around in their heads. I just want people to, every time they read an equation or read about a specific concept or a piece of physics that's happening in a protoplanetary disk, I want this picture to be in the back of their heads so that they can then put it in, okay, this is where in the disk it's happening. And so the top left is a stage 1. So you've got a disk that's still embedded in a cloud, and you've got what that spectral energy distribution looks like. Yes. And then the top right, this is the T-Tauri phase. So this is what we think of when we think of a protoplanetary disk. This is where the planets are growing. This is kind of like, if disks had a main sequence, this would be it.
Very good. Yes.
Yeah.
No.
And then the lower left is the transitional disk. And so there are several hypotheses for how you get these transitional disks, and some of them probably are the result of multiple planet systems. Right. And I have a paper about that, but there are other possibilities as well. You can probably make transitional disks in multiple ways, but it's definitely a sign that something's happening. There's an interesting dynamical process happening in the disk. Yeah. And a planet or multiple planets is probably the explanation in a high number of instances. And so chances are, if you're talking about planetary dynamics, you're talking about this transitional phase. Mm-hmm. So again, just thinking about that, what that looks like, these planets are actually clearing away some of the disk material. And then the last one is the Herbig AE. So this is just the massive star analog to either a stage 2 or transitional. So I mean, most of what we know about disk structure, like the real details of disk structure, is the lower mass, the T Tauri, just because the Taurus star formation region is really close, and that's mostly low mass stars. But high mass stars and disks go through a lot of these same processes. They go through it faster, they accrete faster, they evolve faster, and there's still a lot more that we don't know about those. And I think it'll be really fascinating to study more about planet formation around higher mass stars. I mean, that's an area of research that I think there's a lot of room for new research there.
Very
yeah.
Yeah.
And also in chapter 2, one thing that I really wanted to do, and this is figure 2.5.
No, sorry.
We talk about whether a disk is accreting or not, and that is a big deal. So it's actually before that. Yeah.
Sorry.
There it is. Yeah, that's the one.
My bad. Okay.
So the question of whether mass is flowing through the disk and actually falling onto the star turns out to be a big deal, because it's really telling you how it's one thing that it's telling you anyway is potentially how advanced is your planetary system. Like, do you have giant planets or multiple planets that are potentially choking off the accretion? Is there a binary star, a companion in there that's choking off the accretion? Also, just measuring accretion rates tells us a lot about what time scale do these disks evolve on? So, and how does the accretion work? Is it episodic? Is it more constant? It's definitely episodic. But anyway, so accretion rate measurements are really important.
Yeah.
And I wanted to just highlight for the reader how that actually works and what are you looking at when you measure an accretion rate, because a lot of people who study disks are doing it almost exclusively in the infrared or the radio, but these are going to be UV observations for the most part, and also visible, like with the H alpha line. And so you have to go after it with different techniques, but it's also really, really important, I think, for people to understand how these measurements work. And then one thing that I really set out to do in this book is, so there's a little box 2.2, and throughout the whole book there are these little boxes, which are kind of like, they contain extra information for people who may be kind of new to the subject. It's after this. So there are numbered figures and then numbered boxes.
Okay, let's find let's find.
Yeah, and this is a box on the minimum mass solar nebula, and it has it's after this one. It's box 2.2. Sorry, I actually was hoping that in the electronic edition you could like click on one of these boxes.
I know.
And it would jump out. But anyway, this is the PDF, so that's fine. Yeah, it's this one. So one thing that I really also wanted to do is get beyond the minimum mass solar nebula, because I realized that there are a lot of legacy calculations that are done using the minimum mass solar nebula, but it just doesn't work. It's not physical. It's maybe describing the end of planet formation. It's not describing the beginning. It's not describing most of the process. The minimum mass solar nebula assumes a 100% efficiency of converting solids into planets. And we for sure don't have a 100% efficiency of converting gas into stars in star formation. Galaxies, you've got a lot of gas in the intergalactic medium. So there's no formation of anything in the universe that's 100% efficient at holding on to mass. And we know that about planets too. We have an Oort cloud. There are estimates of what is the mass in the Oort cloud. We see photo evaporation happening. So I really want to move us toward the maximum mass solar nebula instead of the minimum mass solar nebula, because again, all the signs are that the planet formation process is inefficient. We see that happening. We see the waste. And So you have to start out with more mass than is actually going to be incorporated into the planets.
Yeah. Yeah.
So this is a message throughout this chapter particularly, but also throughout the book. All the calculations that I do based on the disk model that forms the basis for this book are done using this maximum mass solar nebula idea.
Okay, cool.
So I think that's the most physically realistic paradigm.
Mm-hmm.
And another thing that chapter 2 features, which was actually something that I hadn't really planned on exploring in so much depth, but I ended up doing it just because what I realized was that planet formation, the beginning stages, are so controlled by the velocity field of the gas.
Gotcha.
And I just realized, given that that's the case, you really have to understand turbulence in disks. And so there's a section at the end that is all about turbulence and the various different types of turbulence that you can have. And so this is actually section 2.4.6 on turbulence, vortices, and angular momentum transport. And that section just kind of like, I wasn't going to make it big, and then it just kind of took me with it. Yeah. But you know, as I was looking in the literature and as I was writing, I was just kind of going there. From observations, we don't have that much information about turbulence. It's been estimated in a handful of disks, but the problem is the turbulence is very subsonic. So it's awfully hard to infer from spectral lines. So you have to really believe that you know the temperature structure of the disk exceptionally well in order to try to measure turbulence speeds in the disk. And it's difficult, and different authors get different results for the same disk. And it's not because anyone's doing it wrong, it's just because it's such a difficult measurement. And it's actually how, for example, how the carbon monoxide is distributed throughout the disk actually can impact the turbulence measurement. Not because carbon monoxide is important for turbulence, but because it's the molecule that people use to measure turbulence from. So, so I put in a lot about turbulence because what I would like people to be able to do is, if you're making a model, if you're a theorist, at least you can make your model consistent with the type of turbulence you're assuming. So you can at least hopefully be self-consistent, and that is easier to do with some models than others. Yes. Because you know, some models predict velocity fields that are very non-isotropic. So that's a hard case to deal with. And then also, conversely, if you're an observer, hopefully you can look at the different types of velocity field you can have, the different possibilities you can have for what kind of turbulence, and then it just gives you more of a context for interpreting the observation. So that's what I was trying to do in this particular section.
Nice.
And there's also, and this is a little bit earlier actually, and I'm going to look up exactly where it is. So this is another one of those boxes. So this is box 2.5 on opacity, optical depth, and intensity. And I put this in there because when I was a grad student, so I only had one astronomy related class when I was an undergrad. And yeah, it's before that. It's, let's see, this is page 2-34. But I think that, yeah, there it starts on page 2-34. That's the one. Yeah.
Getting there. There we
go. So when I was an undergrad, I had a class on astronomical imaging, which was the imaging techniques that you use to do astronomy. Which was it was a very good class, but it didn't really include much physics. So I got to grad school and everybody was talking about opacity. You know, we're going to the, you know, stellar structure class, oh, opacity this, opacity that. And the first time I heard it in a lecture, I was like, what's opacity? I don't know what this is, and I had a unit, okay, centimeters squared per gram, all right. But what does this actually mean? Like, I can use equations with opacity in them, but what does it mean? So I had to go back and fill in those holes. And so,
Physical meaning of it.
yeah, exactly. And so this little section is for people who are in that boat where I was, who,
Good.
need to fill in those holes. So again,
Mm-hmm.
this book is designed to be accessible to students, and students come from different backgrounds. So some students may be very familiar with these concepts. Other students, it might be new. So
Right.
yeah, but
And
I like this particular section.
got some specific intensities going on here. Opacity, intensity equations.
Yeah.
Rosalind means. Yes, very cool. Good, 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 good. Demystifying opacity.
Trying to, yeah. So there's a lot in this chapter, but those are some of the parts that I just wanted to highlight. So we could go ahead and go on to chapter 3, actually, if you want to do that.
Sure, let's slide up and go to chapter 3, microscopic to the macroscopic.
Yeah.
Bubble piles.
So this was interesting for me because this is an area that I have read a lot about, because if you're doing disk work or if you're doing giant planet formation work, you have to understand the first steps of planet formation. But it's also not my specific area of research. So I've more done disks and then also some giant planet formation work where kind of, a solid core is already in place, and then we start adding planetesimals and gas to it. And so to deal with the very first steps was a lot of reading for me, and very interesting. This was also really fun to do. I think that it's really hard to disentangle disk observations. That was one of the main takeaways I got from writing this chapter, because you really have to, if you see a disk in continuum emission, you're looking at the dust, but the dust is moving, it's not staying in place. And so you have questions like, okay, well, here's some dust that's at whatever radius, 7 AU. Where did it come from? How far has it moved? How far is it going to move? What speed is it drifting? So there's nothing static about these disks.
Right.
And so it makes it really difficult from an observational perspective to sometimes understand what's going on in these disks, because, they're like, if you see an edge to the disk in the dust, for example, are you seeing that the grains have moved inward, or are you just seeing that, well, the disk is getting less dense as you go outward, and so the opacity is decreasing, and so you just don't have enough cross section there? I mean,
right.
It's been hard to disentangle, and the observers, I think, have done a really good job at demonstrating that yes, radial drift is really happening, and you have different characteristic sizes for your disk if you look in the dust and the gas. And that's not just due to the fact that, CO molecules give you a giant optical depth, so that it looks like the disk goes on forever in CO. It's not just that. There really is radial drift going on.
Mm-hmm. Cool.
So yeah, and this is also, the turbulence comes back again in this chapter, or in 3.2.4.
Mm-hmm.
And so we could go ahead and look at that section. And this is again very much connecting with chapter 2, and it's how do you take all those turbulent scenarios, all the possibilities for turbulence that you could possibly have, and then determine how do they affect the grains? What do they actually do to the dust in the disk? So I said all those turbulent scenarios. I didn't treat all of them mathematically. I only treated the simplest case. So here are the mathematics of the simplest case in analytical form. And if you want to do something harder, then you need to either extend your analytics or go to numerical work. But this is like, if you're going to try to learn about the behavior of dust under the influence of turbulent gas, then this is a really good start, because it's got all that, it's got the analytical formulation in there. So
Cool.
I think that's an important part of this chapter.
Yeah, because you hit on it there toward the end of this chapter, and I mean, that's a monster topic of how do dust grains evolve.
Yeah, absolutely.
That's a monster topic.
Yeah, and the thing is, the literature is full of conflicting results.
Yes.
So
Science at the bleeding edge.
yeah, it is. It really is. And if you look at the experimenters, they'll mostly say one thing. So the lab experiments with silicate particles really highlight how difficult it is to grow grains.
Mm-hmm.
And that is potentially connected with the fact that if you look at asteroids, for example, you don't see giant constituent particles of asteroids that are mostly made of silicates.
Mm-hmm.
So they're chondrules or millimeter sizes. They're not usually bigger than that. Mm-hmm. But then the paradigm is different if you're looking at ice. But there definitely are experiments with ice, and there are also a lot of theoretical models of collisions between icy particles. But that area of research is newer and it's harder. And so I would say collisions between icy particles are very promising in terms of figuring out a way to get up to the centimeter sizes, but there's more to do. And honestly, if I have to rewrite this chapter in like 5 years, it wouldn't be the biggest surprise to me. But this is kind of the best that we know about at the present. So this is the best synthesis that I could do for you.
Cool. Well, thank you.
And actually, there is a figure that I want to highlight, which is, let's see. So this is another one of those where if you're new to the subject, then coming to grips with this computational and mathematical method is rather difficult, but that's the shearing box.
Oh yeah.
So that's that's in another inset box. So that's box 3.2, and it's on page 3-25.
3-25. Let's go here and up one. There you go. Oops.
Oh, it's before that, I think.
How about right there?
There you go. That's it. Yeah. So I really wanted to put that cartoon in there because I wanted people to be able to picture the shearing box in their heads, because it's featured in so many simulations. So a lot of simulations of planetesimal formation, of dust dynamics. They use the shearing box coordinate system or the shearing sheet if it's in 2D. And this is, again, one of those things where if you're a first year grad student and you read in a paper and it's like, oh, there's a shearing box, and you'll read a ton of papers, oh, a shearing box again and again. And I think it's really helpful to have a picture. So I definitely wanted to put that in there as well.
Yeah, that's a lovely, very nice illustration.
Yeah, thank you. Yeah, that was a fun one to do. And then so there is, there's also a description. This is section 3.2.2 of all the possible collision outcomes. Okay. And, and then finally, section 3.3.3 is about grain growth models. So there is a semi-analytical model in there. So I give the mathematics for that one. This is me summarizing previous work by Till Bernstein and collaborators. But yeah, so the grain growth model section, that one starts with the semi-analytical model. Mm-hmm. So if you want to do, for example, a parameter study, or if you have observations that you want to interpret, then the semi-analytical model is really useful. And then it goes into how to construct a numerical model. And there's kind of a step-by-step on how do you actually do it? Like how would you write a code? There's a sort of kind of pseudocode thing that is in section 3.3.3.2. So
there we go, numerical models, yeah.
Yeah, so it's kind of like a how-to. So
Great.
again, this is my goal of you read this book and you're research ready. You can start doing these things yourself. So
I like that idea, research ready. That is awesome.
Yeah, and I recomputed. There's a really well-known collision model by Windmark et al. 2012
Yes.
that was somewhat updated in 2018, but I recomputed it for a more massive disk, and that's what you see on the top of that figure there. So.
Very cool. Very cool. Good.
Yeah, and we can go on to chapter 4 if we want to.
The last chapter is chapter 4, which is Pebbles to Planetesimals.
Yeah. So what I really wanted to do here was unite the observational and laboratory work on planetesimal formation with the theoretical work on planetesimal formation.
Cool.
And it's so I've gone to a couple Gordon conferences, and those are always fantastic. And I love hearing from the meteoriticists, and I think I've maybe moved on from Meteoritics 101 to Meteoritics 102 now. So yeah, exactly. But I would be interested in hearing feedback from meteoriticists about the planetesimal formation timeline, which is section 4.2. But I really, and there's a figure which is actually really foundational to chapter 4. So it's figure 4.1. And it gives a timeline of when various meteorite parent bodies formed. And then Mars is also on there representing an embryo. Iapetus is on there representing Saturn. So you can use these various meteorite parent bodies, Mars formation models, Iapetus. So the Iapetus model is actually, it's Julie Castillo-Rojas's work, but it's based on the spin down of Iapetus. But you can put together kind of a timeline of when various things in the solar system formed. And so that's a really incredible, it's a very powerful constraint on planetesimal formation models, because you can say, okay, well, this process had to be well underway at this point because, Mars was forming at, 2 million years. And so you had to have planetary embryo forming ingredients available before that. So I had a lot of fun and with this particular section, and originally it was going to be compact, like several paragraphs, but then I just realized it like took me with it. It got away from me, and I just realized I wanted to give a fairly complete picture of the timeline of planetesimal and planet formation in the solar system to the extent that it's even possible to do. So yeah, that is section 4.2. Cool. And then after that, we move on into the theory of how planetesimal formation actually works. And with that, sorry, I lost my table of contents for a second.
Let me get it up here. And
yeah, oh, there we go. Oh, and I wanted to highlight one more thing. So figure 4.3 in this book. So this is relatively early on. I think it's on page 4-10. But this is, you just went past it. So it's a picture of meteorite hunters.
It's in the,
they're in Antarctica, and they're actually picking meteorites off the ice, and then in the right, those are radar tracks that actually track a real meteorite fall. So from airport radar, for example, and weather radar. So meteorite hunting is getting so much more sophisticated, which is great because that means that we get more information about planetesimal formation. So it was a lot of fun to read about how meteorites are found and how the collection of laboratory meteorites has grown over the years. Yeah, anyway, that was something that I really enjoyed, was learning about that.
Yeah, cool.
But in section 4.3, we do the math. And I have tried to connect these mathematical models back to the planetesimal formation timescale, back to what we know about the meteorites. So I wanted to try to put all that information in one place. And then if you're a theorist and you're making a model of planetesimal formation, you can actually look at this timeline of the meteoritic timeline, and you can say, is my model consistent with that timeline? So I really wanted to be able to do that, but this section 4.3 was for sure the hardest to write, because planetesimal formation is a very contentious topic and there are a lot of opinions, but I think at this point, most people agree that there has to be some kind of instability involved. So if you just try to do pairwise collisions between particles, at some point you just get stuck. And describing how the streaming instability works, which is kind of a leading candidate, and then there are lots of variations on the streaming instability. It can happen in the vertical direction, or it can be this way, it can be that way, but there aren't very many conceptual descriptions of how it works in the literature. And yeah, so the streaming instability comes right after this part. So this is just the part where I discuss the self-gravitating pebble layer, which unfortunately doesn't work. But here's where, this section 4.3.2 is where we start the mathematics that gives the foundation of the streaming instability. And then if you go past that a little bit, there is, 4.3.3 on the streaming instability. Oh, that's a good part too, though. So that actually, it shows how you can really get deviations from either a Keplerian flow or the sub-Keplerian flow of dust particles whose motion is totally controlled by the gas.
Yes.
So you don't actually treat any reverse drag from the dust on the gas. So this is the part that actually shows how that happens, what effects start to happen when you get some reverse drag where the dust is dragging the gas along with it. But section 4.3.3 is on the streaming instability. And I really, that's the one. You're there now.
Okay. I like things going to zero.
Yeah, I really wanted to make it intuitive. And I don't know if I succeeded, but I wrote something that I would have liked to have read when I was a grad student.
There you go.
So in a lot of the literature, there's a streaming instability presented. Oh, planetesimals formed by the streaming instability, and here's my simulation, and here's the mass of the planetesimal I formed in my simulation, etc.
Yep.
But in terms of the conceptual, like, how does this happen? Can I picture it in my head? I really wanted to be able to do that for the reader.
Cool.
Yeah, and then also it's an eigenvalue problem, and I wanted to show how the eigenvalue problem actually took shape. Because I think in the original paper on, there's the eigenvalue problem. I think in the original paper on the streaming instability for planetesimal formation, which is an amazing paper, but of course, because it's a journal article, it assumes that the reader is familiar with eigenvalue problems.
Yes.
Obviously you're writing a journal article and you don't go back and do the pedagogy of eigenvalue problems. But if you're teaching advanced undergrads, you kind of need to do that. And so I put that in here. I wanted them to actually see how does the eigenvalue problem come about? So
Good.
yeah, and then I also do consider other mathematics, other models of planetesimal formation in this chapter as well, like turbulent concentration, for example, and resonant drag instabilities. But that's basically, yeah, that's basically the book.
Cool. Very, very nice. Very nice. Well, Sally, thank you very much for walking us through volume 1 of
No
Origin.
problem.
And you kind of touched on it a little bit. And it's kind of hinted at in the title of the book, volume 1. So where do we go from here? Is there going to be a volume 2 that will cover a different aspect of giant planets, or yeah?
Yeah, there is. So I kind of got only halfway through the story in volume 1. So I got us up to planetesimals.
Yeah, okay.
And so volume 1 covers the regime in which gravitational pull between solid objects is not particularly important. So that's a little bit less true at the end of chapter 4, where you're talking about the gravitational collapse of pebble clouds. And so I include analytical criteria for when that happens. But for the most part, everything's controlled by the gas. But in volume 2, we have to start worrying about now the solids. The solids are starting to tug on each other, basically. So I think this is where you actually start separating the giant planets from the terrestrial planets, because most of what I wrote in volume 1 is applicable to terrestrial planet formation. The only exception being that I focused on outside the ice line for the most part. But yeah, volume 2 really gets into the giant planet aspect, and how do you go up the ladder after you have a planetesimal? What do you do from there? So I'm excited about it and also scared about it, because there's a lot more to be written.
Have you started?
Yes, I have started.
Oh, yes, you have.
Yeah.
Very cool. And where can people get a copy of this awesome ebook?
Well, they can get it at the AAS store online. So at store.ioppublishing.org. That's the IOP publishing side, actually. I guess that's not the AAS side.
Right. It's well, yeah, because they're a AAS IOP joint venture.
Yeah, that's right. But store.ioppublishing.org is one place you can get it, actually. And it's also available through the Barnes & Noble website. If you put in Origins of Giant Planets, you can find the book from Barnes & Noble. So yeah.
Very cool. And then for a lot of people, your library may already subscribe to the series. And if that's the case, then you can get a copy of this awesome ebook for free. And it comes in a variety of form factors, from PDF to Kindle to ebook readers, or it comes in a variety of formats. So it's not just a single format kind of thing. So it's very cool. Awesome. Sally, thank you so much for walking us through your really lovely book, and look forward to people teaching with it and using it in the classroom, and then volume 2. So thank you.
Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.